All right, so here we have arrived at another lecture of mine introducing the approximation methods for taking integration. Okay, so this is another lecture that discuss about a different integration technique right here, but instead of getting unlike those other video lectures where I introduce different techniques to get antiderivatives, to get indefinite integrals, here the approximation method here is particularly served, is for that purpose, to get approximated values for a definite integral. Okay, and so before we get started into studying the approximation methods right here, let me now introduce a couple ideas first. So at this point, and I highly recommend that this this lecture here is to be viewed after you have seen my other video lessons on what a definite integral is and how to apply the fundamental theorem of calculus, the second part, into finding the different values of the definite integrals. Okay, but so after you have learned that the fundamental theorem of calculus, the second part, allows us that anytime we're finding the definite integral on a function over the interval from a to b right here, it is allowed, the fundamental theorem of calculus, the second part, allows us to find the first thing, the antiderivative of that function f of x. And so here symbolically I write capital F of x again, so that's just a brief reminder. And then from that point on, we are going to evaluate this antiderivative at the two specific integral bounds right here, integral limits. And then after that, after successfully evaluating our antiderivative at the two value, that we're going to take the difference of capital FB minus capital F at A right here. And this is the work for the work that was enabled, right, by the fundamental theorem of calculus, the second part. Okay. So, and I emphasized quite a few times throughout our lecture there, throughout our study there when we were studying about the fundamental theorem of calculus, the second part, that so the main part here is to find the antiderivative. Okay, so the biggest challenge here, and that's for that reason maybe before this video lessons you might have also arrived at some other video lessons of mine showing various different techniques how to find this antiderivative. Okay. But so now let me put you into another situation. So let me now swing over to the other board right here. And so you can think about a problem as following is brought up to you. We are looking for the integral, the definite integral. We want to evaluate the definite integral of the function e to the x squared dx. Okay, so e to the x squared, and we want to, that's the function, and we want to evaluate this definite integral. So right at the first look, it looks just like any other ordinary integral, definite integral problems out there. Okay, so naturally people would start, and especially once you have learned about what the fundamental theorem of calculus, the second part, is, you're gonna, and of course after you've learned that shocking theorem, that shockingly useful theorem, you're gonna fall in love with that, and you want to start rushing into and use the fundamental theorem of calculus, use the fundamental theorem of calculus. But for a problem like this, how are we going to find capital F of, so my point is f of x here is e to the x squared, but the capital F meaning we have to find the antiderivative or the indefinite integral for e to the x squared. This problem right here produced such a huge challenge for many generations of students. And then when we have to, only when we arrive at a very advanced course in mathematics, when we start learning some more advanced technique to handle this, but within our learning for the beginning integral calculus, this problem is completely a mystery. Okay, so my point now is that it's not always easy to go through that step finding the antiderivative for any function. Okay, and so the consequence now is that the fundamental theorem of calculus got hung up right here. We fail going with that plan using the fundamental theorem of calculus. Okay, and so this is the reason why we start looking over to, so we understood clearly up to this point, and we well aware that the answer to a problem like this has to be a numerical value. Okay, and I have also discussed this in some other earlier video lesson. The answer to a definite integral in general has to be a numerical value. And so for that reason, now instead of directly working through and find an antiderivative, that plan obviously failed according to the problem I introduced on the other board. That's why now we're going to turn our focus, we're going to turn our attention. So at this point, anything we learn is just different options so that we can handle a definite integral problem. Okay, so now when fundamental theorem of calculus doesn't help, right, it's not useful, we have to turn our focus over to looking for some the approximation methods right here. Okay, and so that function I brought up earlier was only one among the challenging one where we can find where it's challenging to find the antiderivative. There can also be a few other ones, and so I can also point out, let's say we have a definite integral from 0 to 1, and our function is the square root of 1 plus x squared, and actually x cubed. Okay, this function, again, if we are rushing into finding, so of course our f of x here is the square root of 1 plus x cubed. But now finding the antiderivative, capital F of x, is a mystery. Okay, it's going to take, I am not saying that it's completely impossible to do, but I am saying it's going to take maybe a few pages only for one definite integral problem. I mean only for one indefinite integral problem, for one antiderivative problem. Okay, and it's might involve very advanced technique that almost impossible for students at the beginning integral calculus to go through, to digest through. So for a problem like this, as soon as we realize we got hung up, we got so much challenge with finding the antiderivative, then the FTC second part, the fundamental theorem of calculus, the second part, is not going to work again. Okay, so here's another example that I would like to point out, that there will be instances out there where the direct work, meaning going through the FTC, the fundamental theorem of calculus, is not helping out immediately. And so we have to turn our focus into looking for some approximation methods. Okay, and so now at this point now, after introducing a few ideas right there, and a few places where it is important to know some of these approximation methods, then I am going to start introducing the idea. So I have to make it clear, and maybe I am the only one formalizing this idea, but you got to understand, no matter how far you are going into because this lecture I am introducing here is only a very brief study of all approximation methods out there for taking the definite integral, okay, for finding the value, for approximating the value of definite integral. There will be an entire field in mathematics for people to learn about different methods to approximate the numerical value of a definite integral. And those courses there, eventually you might end up with a course being a numerical analysis course or any of those courses. So what we are doing here is very basic right there, the very basic stuff. But now back to what I was in the middle of saying, I am maybe the only one, I may be the only one saying this, but at least throughout all of the methods we're about to learn here, they all share one same common or one similarity with the Riemann sum. Okay, all of these shares ideas. Okay, a lot of common ideas it shares. These methods here share with the Riemann sums. So let me bring up the generality as the following. So you have a graph, okay, and the whole idea of a definite integral is that your function f of x inside an interval from a to b, then the definite integral is the accumulation. And at this point, you should be well familiar with that idea that a definite integral is accumulation. And so we started out in our very first day getting to know about a definite integral by going through the Riemann sum. And here we are about to learn the different approximation methods. But I kept saying, and just now I said, any of these methods we're about to learn share quite a few similar ideas with the Riemann sum. And so so we got to look back at the Riemann sum a little bit. The biggest idea in Riemann sums was that we have to break our total interval into subintervals. That's the first idea right there. And then to keep life simple for us, we are going to go with, once we break down our intervals, our total interval into sub-intervals, then we are, to keep life simpler for us, we're going to use an equal width for all of these interval widths right there. And so in that way, so n here is going to be the number, okay, of sub-intervals. And that's one similarity that any of these methods that we're doing has with the Riemann sum concept, the Riemann sum method. Because in the end, Riemann sum that we learned at the beginning was also an approximation method, but the very straightforward one and directly applicable to a definite interval. And so now we're going to take sort of like the more advanced version of that. But no matter how advanced you are going into the approximation method, we have to base ourselves out of these fundamental ideas that we have already seen in the Riemann sum in the days that we study about the Riemann sums. Okay, so again, n is the number of subintervals that we desire, that we want to break our total intervals down. And so, and then in that way right here, as I said earlier, we want equal width. So the width of each subrectangle, the width of each subinterval here is notated as the delta x. And so very similar to how we were doing that with Riemann sum. Each delta x has value b minus a to get the total distance and divide by the number of subintervals that we desire. Okay, and this is how we're ending up with equal width. Okay, we have equal width throughout all subintervals. Okay, so in reality, in the real reality out there, these widths right here don't have to be equal widths, but it's always easier and it doesn't change the final outcome. So for that reason, generations of mathematicians always set out in the convention that we keep equal widths, keeping life simpler for us. Okay, and so that's delta x. Okay, so these are the very core similar idea. And now, so once we have seen that idea, then see the total accumulated area, we're breaking it down. So just similar to Riemann sum like that, we broke it down. So now a little bit brief back right there, a little bit back to the Riemann sum, but Riemann sum we use rectangle, either left endpoint to create rectangle. Okay, that's why I'm dotting my picture. Okay, either we are using a left endpoint to create height of our rectangle, but Riemann sum was mostly about using rectangles. We are erecting rectangles over our subintervals. Okay, but now we are not exactly doing Riemann sums any longer. We are doing other approximations. So, but similar from that idea right there. So instead of rectangles, we are going with, how about trapezoids? See, which is within that space between the first 2 points in my subintervals on this picture right here, we can use we connect a straight line. So that straight line is still not that bent curve over the small interval here, but it's close enough. Okay, and instead of being rectangle like the ideas in Riemann sum, here we're using trapezoids. Okay, and then so here I'm just introducing the ideas, and basically we're using different geometric shapes inside each interval. Okay, instead of rectangles. That's the idea right there. Okay, and so trapezoid is only one plan right there, one strategy right there, and as we go through this lecture over here, this lesson right here, you're gonna see we're gonna even use other geometric shape in each of these subintervals, so that we can approximate, we can keep improving our approximation methods to hopefully keep getting better and keep getting better. And another ultimate idea now is that once we have and so we accumulate, and yes, we have to accumulate all of these areas. So that's another similarity with Riemann sum. So after we broke it down and we decide to use different shapes here, right? And then we're going to accumulate areas. So I am going to quickly erase the board. We're going to have to, but instead of saying accumulate, how about I'm going to say we're going to total all, okay, sub-areas. How's that? Okay, so we broke the total accumulation down into subintervals, and in each subintervals we construct some kind of geometric shapes. on those. And of course, it should be, I mean, once we decide with one kind of shape, we stay with that kind of shape for the rest, for all the sub-intervals. And then we have to total up all sub-areas. And sub-areas, I mean, these are the sub-areas. So we can have about an area 1, an area 2, an area 3, an area 4. And if we have more sub-intervals, we're going to keep adding more. And that's the idea, very similar to Riemann sums again. So Riemann, all that structure of Riemann sum is here. We just here using other shapes, those other shapes rather than the rectangles. Okay, and then after totaling up to get the approximate, now another ultimate idea we have to understand. Okay, as we increase n, the more n. So now allow me to use that symbol as n. And anyone viewing this lesson is expected to have gone through calculus 1, so you are well informed about what this symbol means. We are increasing n to infinity. That means as we keep getting larger and larger n, so the more n we have, the more sub-intervals we reach. Okay, that means we will reach to better approximate, okay, or better precision. That's the idea right there. And so all of that structure with the Riemann sums, I mean, these methods we're about to learn will have all of that generality, okay, from the days we learned about the Riemann sums. Okay, so now let's get to it. All right, so the first approximation method is surprisingly the Riemann sum midpoint rule. Okay, and yes, this is another Riemann sum right here. It is a Riemann sum. Okay, but specifically we choose a midpoint. And so for this particular approximation method right here, I actually have already delivered a detailed lecture particularly on this, because I put this midpoint rule together with my lecture when I was going over all the Riemann sums. So here I only need viewers, or I only need my students to review, okay, just to review my lesson on Riemann sums, because within all of my video lessons for Riemann sum I went over the left endpoint rule, the right endpoint rule, and the midpoint rule. So this was already discussed in earlier video lessons, so there's no need to repeat, because I also covered in a good amount of details there already. So how to get it done, you can review all of the lessons on Riemann sums. Okay, and so there's no need to waste anyone's time to go over this again, to repeat this again. So go ahead and find my other video lessons or my lessons on the Riemann sums and review those concepts there. Okay, and so now so just to mention the midpoint rule is even though it was a Riemann sum problem, but it deserves its place to be regarded as one of the big idea in approximating a definite integral. Okay, so I just mentioned it here, but how to get it done, we don't need to repeat any of those exercises or examples there. Okay, so that should be it for midpoint rule. I will get to deliver more details about the midpoint rule, but allow me to head out to the other approximation methods. Okay? And then we're gonna put it all together, and we're gonna put some more details, ideas together. All right, so after the midpoint rule, right there, basically or essentially that was the Riemann sum. Then now allow me to introduce the trapezoid rule. Okay, trapezoidal rule. And so yes, throughout my earlier explanation in this earlier part of this video lesson right here, I did mention. So the idea again, we have a function with a continuous graph, and this function here, let's say inside an interval from a to b, we want to find the accumulation. So the definite integral from a to b of this function f of x dx is the accumulations, or the visually or graphically represented as the shaded area cumulatively from a to b right here. But now to achieve that, we break that down into subintervals. And for simplicity, I'm using n equals 4. Okay, n equals 4, and so an equal width And so that means each of our delta x here, so that's a delta x. Each one of these is a delta x. Okay, just that idea right there. But delta x, for being simple, for being equal widths, then it's b minus a over n. Okay, and so specifically here in this case, it's 4. Okay, it's 4. B minus a over 4. That's our value of the delta x. And then so as far as the partition point, so I also mentioned the term the partition point. So a is the beginning of our interval. I call it x of 0. That first point right here is x1. This is x2. This is x3, and the last one here is x to the 4th. Okay, I mean x 4th. And this is area 1. But here's the thing. Now the idea of using trapezoid rule is that in the first subinterval, okay, in the first subinterval, then I call that area 1, but area 1 is obtained by drawing that trapezoid right there. Okay, so that's a trapezoid. Now in the second interval, same intervals width right here, same dx, I mean same delta x value, but we have a different trapezoid, but it's a trapezoid. It's no longer a rectangle. So rectangle is, Riemann sum is primarily doing rectangles, but now trapezoid rule, that's why trapezoid rule stands outside of those Riemann sum problem, even though it shares all of that similarities. Okay, it shares all of that generalities actually. Okay, but so now once you can figure out what this trapezoid's area, because so now why trapezoid? Because at least trapezoid is another common shape out there that we do have a definite formula to calculate the area. Okay, and I will get to that. And so with this trapezoid, we call that it's A2. Okay, and so now for the third interval right here, yes, we can connect high end and low end of this interval, and that's in the third trapezoid. We call it A3. Okay, and then in the fourth interval, there's another trapezoid right here. I recognize. Okay, there's a trapezoid. That's the area A4. So we gotta calculate all of these, and then we will accumulate the idea. We will accumulate all of that up. Okay, we will accumulate all of that up. So now let me quickly swing over to my computer to show a more precise graphical illustration of that. Okay, even though I have already done all of that here, but I would like to show a good picture of that on the computer screen right there, so that you will have a better idea. Okay, so here we go in my on my computer screen. The graphing space here is provided with Desmos.com. So the function f of x is whatever that is here. We don't need to worry about what function that is. It has a graph in red. Okay, it has a graph in red ink right here. So that's the curve in red. And now we have an interval between a and b. So the only thing that Desmos is not able to, the only thing Desmos is not able to do for me for now is that how I can put the labels here. So that's A and that's B. Okay, so there's the interval. And so now inside the interval, let's say I'm going with 4 subintervals. So with equal widths. So now these are the 4 subintervals with equal widths right here. Okay, and so now here's how I can see the trapezoids. All right, so here we go. So in between, in this first subinterval right here, and for whatever that width delta x is, that blue line right here connecting my two low point and high point of these two right here, and that creates a trapezoid. Okay, and then so just like that, this other one right here, we have a second trapezoid, and the area in this first one here where I put my mouse cursor at, that's area A1, just like in the picture. And then here I have area A2, the area between the area of this particular trapezoid. And so you can see again, none of our trapezoids here is exactly equal to the area inside of that interval. See, this trapezoid is a little under. This trapezoid is also a little under due to that white space. But this trapezoid, it may be a little under and also a little bit above. And this trapezoid here in the fourth interval is completely above. Right there, but you see, the idea is that ultimately at the end, once we're done with calculating all of these trapezoids, then we are going to accumulate to get the area. So the accumulation, so now I put it in the shading right here, the accumulation of all 4 trapezoids right here will reach to the close enough approximate of the actual area accumulated inside between the curve and the x-axis and inside the interval from A to B. Okay. And so that's the idea of using the trapezoid rule. But so now I'm going to get back to the board and let's really get into it and see how it's done. Okay, and so now I still retain that picture here. The trapezoid rule is quite understandable enough, so I am going to go through to show you how we can derive that. And once we have a core, a detailed understanding of how the formula came out from, then we can start using that formula as a formula. Okay, and so now I am going to swing by to my other board. And let's clear out the board like that. And so now if we're looking at the first picture, so this first picture here allow me to use the red ink to notate that. So with this is rectangle number 1, okay, rectangle number 2, rectangle number 3, rectangle number 4. And so I made a lot of notation, so it's starting to get a little hard to see. I'm going to erase these partition point in black ink right there, but I am going to use red ink for that. Okay, so, and I'm going to erase some of these extra notations here to keep things cleaner for us. Okay, so x sub 0 is this one. Always, it's a convention. X sub 0 is the a value of the beginning point of our interval. Okay, and then in this partition we have x1 is here, x2 is here, x3 is here, and x4 is this value b, the end of our interval. Okay, so that's x4. And so now in that way, once you're seeing that in the picture right here, let's just tackle down right here in the first trapezoid, A1 right here, the area of the first trapezoid. So on my other board, area of the first trapezoid, okay, or A1. So we need a reminder. And the trapezoid currently is looking like this, okay, but it's a better idea that we can set it sideways. So if it's sideways, then you can see that this is base 2, this is base 1, larger base, smaller base. This is height of the trapezoid, okay? And so in that way, here's how I'm seeing it. Area of any trapezoid in general is base 1 plus base 2, base 1 plus base 2 multiplied with height, okay, and divided by 2. That's a famous formula for getting the area of any trapezoid, okay? And so in that way, so now if we're looking at that in our picture, base 1 and base 2, let's find out right here. So for the first trapezoid, base 1 is this function at, so it's the function's height at a or the function's height at x sub 0, okay? And then base 2 is the function's height at x1, okay? And so in other words, now on my other board, this is what I'm doing for area 1. We can just quickly make a sketch right there, or make a chart of the work right here. But it's f of x0, that's base 1, okay? Because it's the height at x sub 0, the height of the function, the height of that point at x sub 0. And then we're going to add with base 2, which is f at x1, okay? And I'm going to, and then that I am going to multiply with the height. In this case, now I'm going to swing back right here in my picture, and the height here really is just that delta x distance. So the height here is delta x, okay? And so for the next rectangle, you can start seeing things a little bit ahead now, but for any of the next the trapezoids, right, the height will always be the delta x, okay? And so in that way, now this is how I'm seeing it. Base 1 plus base 2 multiplied with the height, delta x, and we need to need to multiply with a 1/2. Okay, so one more little step. So that means A1 here algebraically will become, so now I'm looking at the 1/2 f of x0 times delta x plus another 1/2 f of x1 times delta x. So we're done with that one for now. Okay, and so similarly, A2 can be found the same way. So this is how we get the area of the first rectangle. or I don't even have to do this part. I can actually just skip this line right here, and let's leave everything the same way like this with the brackets involved. Okay, we don't need to make things that complicated, unnecessarily complicated. So area of trapezoid number 2 is going to be 1/2 times base 1 plus base 2 and times the height delta x. But let's find out what base 1 and base 2 of area 2 is of the trapezoid number 2. All right, so for trapezoid number 2 is here. Base 1, and really the shorter one, longer one, but base 1 is just, let's say on the left hand side is base 1, but doesn't matter, you can call that base 2 or that base 1 for area 2. It should not matter, but basically we're adding up the two bases and multiply with the height. Okay, so base 1 here is f of x1 plus base 2 is f of x2. Okay, that's all there is, and then height is here the same with the delta x being the height, right? And we have to multiply with the 1/2. And so now in my next one, it's going to be f of x1 plus f of x2. All right, so that's already complete our setup for area 2, area of trapezoid number 2. And then moving on to trapezoid number 3. Okay, trapezoid number 3 right here. Then again, it's 1/2 times base 1 plus base 2. I'm leaving that empty brackets right there. Multiply with the height dx. Okay, the height of the rectangle of the the height of the standing up trapezoid right there. And that's why that's with the dx now becomes the height of our trapezoid. And let's look back at our picture. All right, so with our picture right here, x2 is here, x3 is here, that creates the height between them. Our trapezoid is like that. So base 1 is f of x2, base 2 on this area is f of x3. Okay, and so in that way, I am seeing that it's f of x2 plus f of x3. Okay, and so now we're at the third trapezoid already. The fourth one is ready on the go right here. All right, so again, it's going to be a 1/2 times base 1 plus base 2 times height delta x. Let's now look at the picture to see what base 1 and base 2 are going to be like. All right, so now my base 1, so for the fourth trapezoid here, base 1 is this line right here, which is f, the height at the function value at x3, and this is the function value at x4 right here. So base 1 plus base 2, so f of x3 plus f of x4. Okay, so now in our part, f of x3 plus f of x4. Okay, so I've made a sketch of all of these separate trapezoid areas. These are all the separate trapezoid area. So those are the distinct individual ones. Okay, but again, ultimately we need to total up. We need to total up just like the idea of the Riemann Sum. We have to total up all of these parted areas. Okay, so that means A1 plus A2 plus A3 plus A4, that gives us the approximate. Okay, so now I have to erase some of the work here so that I can write my final area. Okay, so go ahead and take note on that, and then so now A1 plus A2 plus A3 plus A4, that's the next step. Okay, so that means it's a 1/2 times, now allow me to write small, f of x of 0 plus f of x1, okay, times delta x. I'm going to add with, this is for area 1, 1/2 times the base 1 f of x1 plus f of x2, okay, times delta x, plus, so that's area 2 added in, okay, and then I'm going to add, okay, 1/2 times base 1 being f of x2 plus f of x3, okay, times the height delta x plus the area of the fourth trapezoid. So 1/2 times f of x3 plus f of x4 times delta x. Okay, so now with all of these four areas, all of these four sub areas that we are totaling up, at least they all have a common factor. And so by the way, this total sum here is the trapezoid approximation method. So I use a capital T letter over here. And specifically in this activity, I am going 4 sub-intervals. So, or consequently, we produced 4 trapezoids for us. So it's T4. That's how we call it. Okay. And so now, here's how I'm seeing it. A little more algebra to be used here, and we can realize that we have a common factor of 1/2 times delta x, 1/2 times delta x, 1/2 times delta x, 1/2 times delta x. So we can factor it out and turn our expression into something a lot simpler. So T4, in other words, will equal to, in the next step, it's a delta x over 2. Because 1/2 times delta x is a delta x over 2. And then I'm going to open a large square bracket, a large pair of square brackets. So now all of these inside the square brackets going to go into this huge pair of brackets of mine right here. Okay, and so what I'm looking at is for the first pair of brackets right here, I'm looking at f of x of 0 plus f of x1. And then for the next pair of values right here, the next sum right here, I'm going to bring that in, and so I'm looking at adding another f of x1, but plus f of x2. And then I'm going to bring in this third pair of values right here. So f of x2 plus f of x3. Okay, and I need a little more space here. So I'm going to add, okay, and the last pair of height right here, f of x3 plus f of x4. And I close my bracket there. So that's the summing up of all the height right here. Okay, and after I have already factored out the delta x over 2. Okay, so from this step here to this step, it truly reflects the fundamental. We're summing up all of the little sub areas. Okay, but here it's just a little extra algebra work on top of what we have produced. Okay, but now if we're looking at this, the sum inside of our bracket, it looks like we can rewrite that in a simpler expression. Okay, so allow me to just erase this line right here. But you can notice we have only one f of 0, only one f of x4, but all of these x1, x2 right here, there are 2 times, 2 times, and 2 times. Okay, so in that way, in my next step, that's where I'm going to save some space right there. And so f of 0, the very beginning point of our interval, that's the impact of this. But so that's only coefficient 1, but anyone in the middle, f of x1 and so on, that's 2 times. 2 times of f of x2 plus 2 times of f of x3. Okay, but when we reach to f of x4, which is the last one of our interval, that's only back down to 1 time. All right, so now at least for using 4 subintervals, we have now come to a final cleanup formula for the trapezoidal method, the trapezoidal rule to approximate the area. So what I'm saying now is that the accumulation from a to b on whatever function f of x, okay, can be approximated by this T4. Okay, so T4 is this formula right here. Okay, and the 4 is the form represents 4 subintervals that we are using. Okay, and so if we let's go ahead and observe this formula a little more closely. Then so on my what if we are in a general case here, in a general case where we have more than 4 subintervals, because here I'm using a specific number of subintervals being 4 here, but in general, what is the formula? Okay, so now I have to erase the picture because I need to make space for writing my next general formula. So here, concluding from that earlier formula, then you can see that T sub n right here, that means the trapezoid method, the trapezoid approximation method, or the trapezoidal rule over here for using generally any n number of subintervals. Then we can always have that delta x over 2 in front. Okay, and with a pair of brackets. So just like that, this is what we were looking at right here. This is what we were having at our final formula for T4. So T4, it's delta x over 2. And in the brackets, now inside the brackets, the first point of the interval and the ending point of the total interval from a to b stays with coefficient 1. See, 1 times of f of x is 0, and 1 time of f of x 4. But now on any other partition points between the beginning point and the ending point, then any of these guys right here have coefficient 2 right there. Okay, so now in that formulation, we're going to start recognizing a generality right here. And so let me advance to the other board and complete my formula for a general case where we have some n subinterval, some general n subinterval. So here we will, f of x of 0 is here, coefficient 1. But plus, now starting here, it's 2 times f of x1, plus 2 times again f of x2, plus, and I don't know how many more times, but 2 times, still 2 times of f of x sub n minus 1. Okay, and then to when we reach the last one, it's only 1 time f of x of n. So f of x of n right here, x of n, remember, in your interval from a to b when we're doing that accumulation, then this is x of 0, and this is x of n is your b value, the final point of the total interval. That's the idea. And then we might break it down into n subintervals. So number 1, number 2, number 3, number 4, all there. Okay, and so this is the formula for the trapezoid rule here. Okay, and that's the formula to highlight for the day. Okay, and so of course delta x generally is going to be b minus a over n, because we want to maintain the equal width here, and n is the number, okay, number of subintervals. All right, that's n is the number of subintervals. Okay, and so now just in that way right there, you can see that as we're attempting to get the exact answer on this definite integral of the function f of x over the interval from a to b, then that the answer to that definite integral can be approximated. That's why I'm using this symbol over here. So that means once we calculate our Tn, then our definite integral will be approximately equal to the approximation that was done using trapezoidal rule right there. Okay, so that's another thing to keep in mind. We will never, none of our Tn right here, none of our trapezoidal rule answer is the exact answer. It's only an approximate, okay, to that actual answer of the numerical answer of the definite integral here. Okay, but think of that. On the other hand, the more n we can reach, the better that is. Okay, the better approximation we will get. So one more time, let me swing over to my computer screen right here, and I'll show you the picture again. So with that beginning problem that I brought up, then we had 4 subintervals, but now allow me to increase. I'm going to increase to 10. All right, so now each trapezoid of mine looks already so close to the curve itself. Okay, and so now and so if we spend some time doing this calculation of accumulating up all the trapezoid areas here, then it's going to be something that's real close to the actual area between from A to B between the curve in red and the x-axis. And now I'm going to increase to, let's say, 60, and I can't really tell anymore between the trapezoids and the curve itself. It looks so fine. And now when we get to like 260, okay, then this area right here is really just like the actual area, even though it's 260 there are 260 sub-trapezoids in there. Okay, and so let me really zoom it in at a very extreme level so that you can see it. Okay, unless I bring it in at very extreme level, and at the very extreme level, almost to the point that decimal cannot zoom in anymore, but we can still see that with our human eyes no difference between the trapezoid and the red curve right there. Okay, and that's the idea of using the trapezoidal rule right there. And so just like the Riemann sum, it's always like that. The more sub-intervals that we can break, okay, the more sub-intervals that we can divide out, Okay? The better the approximation is going to be. Okay, and so now at this point, let's take a break from the rules right here, from the approximation method. Let's do an example. Let's look into an example directly right here on this trapezoidal rule over here to have some hands-on experience for us. All right. So now I'm going to erase the board. All right. So here we go. Let's look at example 1. All right. And so our example 1 right here, I'm going to get pretty straightforward. We're going to approximate. Okay. And here you go. I introduced for you that integral where I mentioned earlier in the beginning of our lecture over here. That integral from 0 to 1 on the function e to the x squared. Okay. So e to the x squared is a function that is very challenging for getting the antiderivative. So as I have already mentioned earlier, the route that we use, if we're going in that route by using the fundamental theorem of calculus, the second part we will definitely get hung up, at least at our level right now. Okay, because it's not easy, and we have to wait until a very advanced course in mathematics to know how to find the antiderivative there, and it's going to be a completely separate strategy to get the antiderivative there. Okay, and so in that way, now we're going to approximate that answer. Okay, so computers in these days are all programs with some advanced techniques to get the exact answer, but here we are using so that's why, if you're using a computer algebra system, a CAS, computer algebra system, usually you get the exact answer. Okay, but think about this. If you're asking to yourself, how does the computer know that exact answer? The engineer who wrote the program to calculate this use either one of the approximation method and keep asking the calculator or the computer to increase the number of subintervals and increase the number of subintervals until they start recognizing a final pattern that leads to a final answer right there. Okay, so for us here, we're going to do things completely from scratch and think about that. Any one of our answer here is going to be an approximate to the real area here, the real answer there. Okay, and so now I'm going to approximate this. Part A. How about approximate that integral using T4? All right, so now allow me to start using that symbol intensively now. So T4 here means I want to approximate that using the trapezoid method or the trapezoidal rule. So we had that formula specifically designed. Written down on the board earlier. And then I want specifically 4 subintervals, okay, in between 0 and 1. All right, so let's get the easy parts down first. T4 means n equals 4 subintervals, okay? And that means each of our delta x here is going to be final point A final point B minus beginning point A in our interval. So 1 minus 0 over 4 subintervals, okay? That's how big each of our delta x is. So this is delta x is going to be a 1/4, right? Or if anyone likes to use a decimal value, it's 0.25 for 1/4, okay? And so now that means, and it's never a bad idea at all to quickly sketch down the picture of the partition points, okay? Just like that idea that I introduced back in the days we studied about the Riemann Sum. So just that little segment right there. 0 is the beginning and ending point at 1. This is our interval from 0 to 1 right here. And this time we break our interval into 4 subintervals. So halfway is here, quarters are here. Okay, and of course we have to forgive ourselves about being a little bit upscale here and there. We're not machines, and that's not the point. But the picture will give us a good idea of how we can plan things. So now that point right here has to be a 0.25 because it's that space 0.25 from 0, and then here's a 0.5. This is a 0.75. Okay, and then yes, this is. This point right there, right at 0, that's x sub 0. This is x1, this is x2, this is x3, and this is x4. Okay, so that's how I'm seeing it. And so now, and all of these delta x here, any of these delta x is that same amount of space being 0.25. Okay, and so now I am going to navigate to the other board, quickly erase out the board, and and then we're going to work on that. All right, and so now, so the formula for T4 should be, so it's delta x over 4, okay? I mean over 2. Delta x over 2, and this is eventually will be a 0.25 for delta x. But I'm just gonna write down the generality of the formula first, the general formula first. So f of 0 is always coefficient 1. But f of 1, starting with f of 1 and anywhere before the last one, which is x of 4 in this case. And that's why it's always a good idea that we can have the picture of the partition pointer here so that we know which one is our last one. So our last one here is x of 4, but that has to be coefficient 1, okay? So now f of x of 4 is the last one in our brackets, coefficient 1, any other ones in between from x1 to x3, we have to go with coefficient 2. So what I mean now is that it's 2 times of f of x1 plus 2 times f of x2, okay, and plus, and I realize I need a little more space between, so I'm going to write these a little smaller. 2 times f of x2 plus 2 times f of x3, and that's how I'm writing it down, okay, and that is the trapezoidal rule right there, the general formula. And so now we already had everything laid down. So delta x here in this case is a 0.25, okay, and that's over 2. All right, so now f of x of 0 means we're looking at, and x of 0 is 0, so it's e to the 0 square. That's f of x of 0, okay, plus, and by the way, yes, our function is f of x equals e to the x squared, in case I forgot to mention, and I did forget to mention. So f of x is e to the x squared, that's our function, okay. And so, and now 2 times, so 2 times f, the function is e to the x squared, so f of x1 now is going to be e to the 0.25 square. This is x1, but f of x1 is e to the 0.5 all square, okay, and then with a coefficient 2. All right, and so now plus, and now here I'm looking at 2 times e to the, and now my x2 value is going to be a 0.5 according to the chart I've had earlier in square. Okay, so just to clarify, it's right here, x2 is that point like that. See, so sometimes it slows you down, it might slow you down a little bit, but get the safe work right here to lay down all the little details is always a useful idea, it's always the best idea like that, so that you know exactly what you need and what you are doing, okay? And so x3 is there, and x4 is the last one, so I won't be able to swing back and forth much, but you can always pause the video and take clear notes like that, okay? And so plus 2 times e to the 0.75 square, okay, but plus, and the last one here is just only 1 time, so e to the 1 square, okay, and that's how I'm setting it up right there. And so at this point, everything is just up to us to use the calculator and getting it done. Okay, I am going to step over to my computer, my calculator on the desk, on the computer desk, and get a final answer for us. All right, and so now I have the answer to be calculated together. It's 1 point, so this is T4 here, 1.49067888617, and a lot longer. Okay, so I used decimal as well to get that calculation value done, but so this is the answer to T4. All right. All right, and so let's look at another calculation problem right there, another computational problem. So here we're looking at part B of our example. So the same integral over here, but just to get anyone comfortable with the idea of, and just to get yourself faster with the trapezoid method. So how about let's use, so I'm going to call that part B, just another practice opportunity right there. So how about we're going to approximate that using T6. Okay, and so n equals 6. Trapezoid method, okay, trapezoidal rule, 6 subintervals, and we are working, so each of our delta x this time is going to be 1 minus 0, but over 6 right here, which is a 1/6. So allow me to use fraction here, because otherwise in decimal it's going to be a very lengthy the decimal and repeating decimal. So I like to write that as a 1/6 here. Okay. And so now what I'm seeing here, once again, as far as the chart that shows all the partition points right here. 0 is the beginning of our interval ending at 1. So halfway is here, and each one of these we have to break it into the thirds. Okay. All right. So this is a 1/6. This is a 2/6 or a 1/3. Okay. This is a 1/2. Okay. This is a 2/3. Okay. This is a 5/6. Okay. And this is a 1. So those are the partition points right there. And again, as a numerical label, I am going to write down, see, this is x sub 0. Our last one here needs to be x6, just like that. I want to show the correspondence between the last, how we call the last point, and the number of subintervals we need. So the last one, as a convention, is always a x6 if we're going with n equals 6 like that. Okay, and then the very beginning one is always a x sub 0. And then any of the other guys in between is going to be x1, x2, x3, and so on and so on. And so this is x1, this is x2, this is x3, x4, okay, and x5, the very last one before that. All right, so we now ready for heading out to the other board. All right, so now let me quickly write down the formula for T6 right here. So T6 is going to be, again, delta x over 2. And I'm going to open a square brackets, f of x 0 with coefficient 1. So 1 times f of x 0 plus, and then 2 times f of x 1. So anything starting with f of x 1 all the way to f of x n minus 1. Which is in this case right here, anything that goes up to f of x to the x5 here, those are all with coefficient 2. Okay, and I'm short of space, so allow me to write the dotted, the horizontal dots right here, the 3 dots between those. And then the last one is f6, f of x6 right there, okay, with coefficient 1. That's how we're doing it. Okay, so everything here is repeated of the 2 times of the function. Okay, so x1, x2, x3 up to x5, those are all with 2 times. Okay. All right, and so now we are ready. So that means we're looking at a 1/6 but over 2, so it gives me a 1/12. Okay, and then the function, we already knew the function, so it's e to the 0 square. That's but coefficient 1, so that's f of x of 0. X of 0 in this case, according to our chart previously, that is 0. Okay, and then 2 times f of x1. So x1 is a 1/6. So 2 times e to the 1/6 square like that. Okay, so once again, I just need to remind everyone about this. So this is x1 right here. So x1 is being a 1/6. Okay, and so, and now 2 times e to the 1/3, because 1/3 is our x2 square. Okay, and then plus 2 times e to the, and then 1/2. This is, so x1, x2, x3 is 1/2 squared. Okay, plus, and then 2 times e to the 2/3. That's x4 square. Okay, and then plus 2 times e to the 5/6 square. And this is x5 right here. So 2 times f of x5. And then last one here is only 1 time, coefficient 1, e to the 1 square. Okay, and that completes our setup with all the numerical values successfully substituted in. And now this is ready for calculation. So again, I am going to quickly step away to my desk right there for a calculation, and I will be back with the final answer right here. All right, and so my calculation came out from decimals 1.475 178 71435. And let me double check again. All right, and a lot longer. And that would be our approximate. Okay? And so I should have labeled this from my earlier problem, but I forgot, but here I can just do that. The integral, that means the integral from 0 to 1 on this function e to the x squared dx can be approximated, okay, to this value right here being 1.475 1788 and a lot longer. Okay, so that's how we're doing it. Okay, all right. All right, and so this is something worth it to share right here. So as I have mentioned earlier a little bit, that so you don't have to question about this yet. You will arrive one day, any one of you will arrive at a course where you teach computers, okay, how to calculate these exact value. But now assume now that I already had the calculator, the computer that knew the exact answer on this definite integral. So let's now call that I, okay? The exact answer for I here, this definite integral, according to my calculation on the computer, then it's a 1.46265 174,591. Okay, and it could be a lot longer as well, because in the end, you know, even computer, and we believe this is the exact, and let's assume it is the exact one. And like I said earlier, one day any one of you will learn how to teach the computer to get this exact answer right there. Okay, but now if this is the exact answer, then you can see that if we recall that our T4 was 1.496. I mean 906. Okay, 788 617. So we got already pretty close. We are about 0.03 away. Okay, from the exact answer right here. So this is the exact. This is the approximation with 4 trapezoids. And then we increase to 6 trapezoid. So T6 gave us, and the answer is still there on my other board right there. And I can quickly swing back for any one of you to have a look at. So this was the answer from T6 right here. And so so this integral is approximately equal to that. And so now I'm going to go ahead and write it down. So 1.475, okay, and 1787, 1435, so, and a lot longer. So any of these. So now you can see that as we increased the number of sub-intervals, and consequently we produce more trapezoids, then we're getting to an answer that, and then our answer keep getting closer and closer to the exact area, the exact the answer for this definite integral, right there. So just like that, how I mentioned in the earlier part of this video, and then as we allow n to increase, the number of sub-intervals to increase, we will get a better approximation. Okay, and we will keep getting a better approximation. The positive side of doing approximation methods for integration, for definite integral, is that it's always true that the more we increase the number of sub-intervals, the better approximation we get, and we know, you know, whether we had, I mean, we know where we're heading. Okay. We will get the better approximation. Okay. All right, and so now let's look at another approximation method right here. So just now we have learned about the trapezoid rule. So now I'm gonna introduce another approximation method for a definite integral, and this method here is called Simpsons. Okay, it's a Simpsons rule. All right, and so before we get into the Simpsons rule, so take that as just another the approximation method here is similar to the trapezoid, but instead of using trapezoids in each subintervals, now we're going to use a different picture in each of the subintervals. Okay, and so, but also a couple of things I have to also really mention. The Simpsons rule only work for, so yes, n is the number of subintervals. So Simpsons rule, anytime we're working with Simpsons rule, n must be even. Okay, n must be even for the Simpsons rule to work. Okay, so that we can only go with 4 subrectangles, 4 subintervals, 2 subintervals, 6 subintervals, 10 subintervals, or 8. But the Simpsons rule is not going to work with n equals 9. Okay, so Simpsons rule has a little bit of a limitation right there in a sense of the number of subintervals must be an even number. Okay, and then here's the idea, but Simpsons rule is a little harder to explain in detail. So I will just give a picture explanation, but then the work to derive the formula of the Simpsons rule is delivered within any standard calculus textbook. So save me from mentioning those here. So I am not going to go over the work to derive the formula for the Simpsons rule. Okay, because it's written in all over the textbook and it's a little lengthy. So introducing that in a video lesson like this is a little bit too much right there. Okay. But now at least I still gonna brief through the idea. So the same fundamental earlier, we have a function f of x with a curve being drawn in the board here, and we have an interval from a to b. Okay, and we're gonna break our interval into, let's say, and now we strictly require only an even number of subintervals. So there we go, 4 is a good place. So let's say n equals 4. Okay, and so the delta x here, each delta x is a b minus a over 4, or n in general. Okay, and so this a is x0, this is x1, this is x2, this is x3. Okay, and then of course b is the last point of our total interval is x sub 4. See, it's always consistent that, the last value here is with the subscript that consistent with the number of subintervals that we're looking at in our problem. Okay. But so now here's the idea of the Simpsons rule, and allow me to use a blue marker, color marker here. So inside of each subintervals like this, Riemann sum used rectangles. Trapezoid rule we've learned previously use a different shape, the trapezoid. Okay, and so Simpsons rule use a parabola. Okay, so right in between these two tip points right here, Simpsons use a parabola, and that's why without the precise laying down work, I'm not able to draw the exact picture. But see the parabola I'm trying to draw in blue ink right here. So some parabola is and here the part of the curve is concaving down, so the parabola in that area is also concaving down right there. Okay, so some parabola and close enough to the bent shape of that particular interval. Okay, the bent shape of that part of the graph inside of that interval. So just like that, it's not a trapezoid, but now we have a picture, an irregular shape with a piece of parabola here. Okay, and recall for yourself, a parabola came from a quadratic function. So basically we use some kind of quadratic function that goes through these 2 points in this particular interval right there. Okay, but like I said, all of that details you can find that in any of your standard calculus textbooks. It has all that explanation here. It's just a little too much for me to mention that here in this video lecture. I want to keep it somehow focused to the main point of what we're doing. So now in the next subinterval, and by the way, so yes, once we had that parabola, that piece of parabolic curve right here, we're trapping our intervals, and here we create an area, and we call it A1. Okay, so just all that fundamental ideas, and then there's A2 is here, and we're gonna use see the shape here is already bent, but we're gonna use some kind of parabola that maybe it's down below here, but some parabola in blue that approximates that curve like that. Okay, and then so we have an A2, and then now we're gonna look at see this part of the graph right here. It looks like a concaving up piece of shape right there, a bent curve. So I'm going to use it's going to have to be approximated by a parabolic shape that's a concave up. Okay, but what exactly is the equation for that parabolic shape in there? You know, the calculus textbook of yours will have a better explanation of that. Okay, and then here in this, and we create an area A3. Okay, and so we're still summing all of these areas here together. And this last one, yes, it's another concaving up parabolic shape right here. Okay, and the parabolic shape doesn't have to be continuous one, because I'm not saying that this is all one parabolic shape. It's just different parabolic functions, different quadratic function here that only fit inside of these intervals. Okay, but then so once we're looking at that, then, and again, just like what I was saying earlier, the actual explanation, the actual formula for all of these, and the actual detailed explanation is delivered in all throughout all standard calculus textbooks. So allow me to skip that part, but I'm going to write after from this geometric figure of this, and to describe the situation of how Simpson came up with that. Okay, then I'm going to get straight into delivering the formula. And so the formula for the Simpsons method to approximate the area inside of a curve is as following. The delta x, okay, divided by 3, and I'm going to multiply that with, all right. So f of x of 0, the very first point in our interval, coefficient 1, so f of x of 0, just like that. Okay, and then the next one, starting with f of x1, I'm going to go, so f of x1, but I'm going to multiply with a coefficient 4. But then it's going to start alternating. So after the 4 coefficient, the next one is f of x2. It's going to alternate from 4 down to 2. So plus 2 times of f of x2. Okay, but I'm going to alternate back to 4. So only the very first one here is coefficient 1. The later one, starting with x1, is going to alternate starting with 4, and then 2, and then 4, and then 2. Okay, and so 4 times f of x1 plus 2 times f of x2. So the next one here, guess what? F of x3. So it's going to be 4 times. So on all of those odd index, okay, other than the last one, so all of those odd index right there, okay, then those are getting coefficient 4. That's another way of seeing it. Okay, and all of those even index other than the first one and the last one, those are all coefficient 2. So plus 2 times f of x4. See, this is what I mean by the even index right there. Okay, so on all of those even indexes, we have to multiply with a coefficient 2. Okay, and then I'm going to keep adding. Okay, and so in this alternating pattern, then the very last one here, the very last one, x of n, we'll get only coefficient 1. Okay, the very last one. See, x of n is always consistent with the number of n sub intervals. So here in our particular demonstration here, 4 sub intervals. So the last point is x4 being consistent with n equals 4. But then that means the partition point right before that, namely x of n minus 1. Now that's going to be an odd index right there, because this is even for sure. We have an even number. We're always going to use even number of subintervals. That means n has to be an even number. So this n minus 1 index has to be an odd number. So on odd index, we have to always go with 4, with coefficient 4. Okay, and so in that way, that completes our formula for the Simpsons rule, generally given at some n subintervals. And I have used the notation S sub n before. Many textbooks use S sub n for Simpsons rule, but I have used this symbols before in my lecture, in my general lecture about the Riemann sum. And so in that way, allow me to use a notation slightly different from many textbooks out there. I'm going to use SS, Simpson, okay, with a subscript n right here. So the Simpsons rule at n intervals, with n subintervals, is given with that formula. Okay, delta x over 3, and multiply with that lengthy sum right there. Okay, and that is our formula for the Simpsons rule. All right, and so again, once we complete with a Simpson rule using any specific number of subintervals right here, then it will never be the actual answer to our integral problem. Our definite integral problem can only be approximated by the answer that came out from a Simpsons Rule calculation using n subintervals. Okay, and so that's another thing to constantly keep in mind for yourself, like that, to constantly remind yourself. All right, about any approximation method, the answer we have for approximation is only an approximation. It's only getting close to. Okay, and then later on we will explore again the further, the more n subintervals, the more we increase n, right, the better approximate we're gonna get. Okay. All right, and so now I'm gonna be erasing the board, and surprisingly we are ready for another example. So to continue with our earlier example, I'm gonna call this now example number 2. All right, and so here we go, example 2. And I am going to utilize the exact same function because it was a challenging function to go through with the antiderivative route to apply fundamental theorem of calculus, and that's what brought us into all of these into exploring all of these different approximation methods. Okay, and so allow me to and I purposely use the same function so that later on we can compare, you know, efficiency on any of these. Okay, on some function, this method, this approximation method wins better efficiency compared to the other ones, for example. Okay, so I want to approximate. Okay, I want to approximate this integral from 0 to 1 on the function e to the x squared dx. As I said, same exact function. So that means our function here, f of x, is e to the x squared. Okay, but I want to approximate that in part A. How about using Simpsons Rule with 4 subintervals? Okay, so keep in mind, we will never, and no one will ever ask you for SS5 because we can't go with Simpsons Rule on an odd number of subintervals. We can only work with an even number of subintervals. So you never have to worry about this. Okay, so that's something I can surely cross out of our work list right there. Okay, but now SS4. Okay, so that means n equals 4. Okay, and our delta x, each of our delta x here, the interval is from 0 to 1, so our delta x value has to be 1 minus 0 divided by 4, and that gets us a 1/4, or numerically 0.25. All right, so we have that, and it's a good idea that we draw for ourselves the segment here representing our interval from 0 to 1. So 0 is the starting point, 1 is here, halfway is exactly in the middle, so quarters are here. Okay, so now we got the first, this is 0.25, this is 0.5, this is 0.75. It's easy enough to see these partition points there. Okay, and so now as far as the label, then right at x of 0, right at 0 right here, that's our beginning point of this integral interval. Then this is x0, so we got 4 subintervals here. So here I'm looking at x4 as the last one here. Okay, and then all of these guys between, there's x1, there's x2, there's x3. Okay, and so again, recall for yourself, there are some odd indexed partition points, and there are some other even indexed partition points. Okay, keep that in mind, because we need to, when it gets to Simpsons Rule, it does matter a little bit in terms of the coefficient, right? And you have seen that through when I was explaining about the formula. All right, so now I'm going to get over to the other board. All right, so to fire up SS4, the Simpsons method for 4 subintervals, and to estimate the exact, to approximate the exact definite integral here, I'm going to go with so 0.25 is our delta x, but over 3 according to the formula. Okay, and then I'm going to multiply with, so this is f of x of 0. Okay, and we only go up to f of x of 4. So here's how I'm laying it down. So it's an awesome idea to always lay down the formula first, the general formula first. So I shouldn't even rush into this 0.25. How about just write it down as delta x over 3 right here. Just remind yourself about the formula for the Simpsons Rule, and with 4 subintervals. So x sub 0 is the first one, always coefficient 1, and then plus. Now this next one immediately comes with the f of x1 odd indexed. Okay, so this is coefficient 4. Okay, but now the next one here is f of x2 even indexed, coefficient 2. Okay, start seeing a generality on that. And now so the next one here is going to be f of x3 is another odd index here again. So this is coefficient 4. Okay, and now the last one here is f of x4, which is also the last one. We leave a coefficient 1 there. That's the formula. That's the formula for the Simpsons method, right? Based on or using 4 subintervals. And now we're ready for properly substituting values in. Okay, so delta x is 0.25. So I'm going to go 0.25 over 3, and that's what I wrote down accidentally earlier, a little rushly earlier, and then I erased that and changed to this. And then the function is e to that famous scary function e to the x squared. So now I'm looking at e to the 0 square coefficient 1. Okay, because once again, see, having this chart is an excellent idea right here. The chart here will lay down all of your partition points with values like that. Okay. And so now I'm looking at so that, and then the next one here is 4 times. So 4 is because of that coefficient proven in the formula. And now we're looking at e to the, so 0.25 squared. Okay. And the next one here is going to be f of x2. So f of x2 is e to the 0.5 squared. Okay. 0.5 squared, but only with coefficient 2. Okay, and then f of x3 is going to be e to the 0.75 squared, but 4 times, because anywhere we hit to an odd index, the partition point, odd index partition point, then we have to multiply our function at that value with a coefficient 4. Okay, and then other than that, those are the 2, and then the beginning one and the last one. So the last one is coming now. It's e to the first power squared, but coefficient 1 on the last one. That's how it works right there. Okay, and then so we add with that. All right, so that's how it works. All right, so now at this point, all I have to do now is just to quickly step over to my computer station and graph a final answer for this, and I should be back shortly. All right, so with the computer, with the answer that generated by my computer, I'm looking at 1.46, 3710, 76043, and it could be a lot longer. But that is, ladies and gentlemen, this is our answer for the Simpsons rule at 4 with 4 subintervals. And that's the answer to that. And so now that means the actual answer, the definite integral from 0 to 1 on the function e to the x squared, can be approximate or approximately close enough to this answer here, 1.46, 371076 and a lot longer. That's what it means right there. All right. All right, and so now part B, just another try for everybody. Just another try for everybody to get successful, to get pretty fluent with using the Simpsons rule. So I want to approximate the exact same definite integral again. And in part B, and you can start working independently as well. As I'm going through the steps here, you can treat this problem as an FYT, as a problem where you're working on your own as well. So part B right here, I want to approximate this using Simpsons rule, but with 6 subintervals. Okay, with 6 subintervals. So once again, let's lay down the information we need right here. N equals 6. It's an even number. Okay. Delta x has value, so 1 minus 0 divided by 6, which is 1/6. And so now when it gets to some fraction like this, allow me to write it in fraction rather than writing that in decimal, because it's going to be very lengthy decimal and repeated decimals. All right, and so now here's the picture of my partition point right here. 0 is here, 1's there, okay, and all right, so here I'm looking at a 1, 6. There's a 2, 6, which reduces down to a 1/3. There's a 3, 6, which reduces down to a 1/2. There's a 4, 6, which reduces down to a 2/3. And there's a 5, 6 here. That's how we can quickly get the partition. And so yes, again, the very beginning point, I call it x of 0. Okay, the very ending point here, there are 6 subintervals. So this one here is x6 is the last one of our interval. And any of these is starting with x1, x2, x3, and so on. So x1 is here, x2 is here, x3 is here, some indexed partition point, or some index here are odd, right? And we had some even indexed point right there. So be aware of those guys right there. So x4 and x5. Right? Some partition points fall right on the odd index, and some others partition points fall right on the even indexes. Okay. And so now once we've had the picture of our partition points, we are completely ready for getting that work. I'm going to quickly erase the board. All right, so using 6 subintervals, here's my formula for the Simpsons rule. F of x0 stays with coefficient 1. F of x1, this one has odd index. This one here has odd index at the partition point, so I have to multiply that f of x there with coefficient 4. The next one here is an even index on the partition point. We multiply with coefficient 2. Okay, and then 4 times f of x3 odd index on the partition points again. We keep adding those. Okay, keep adding those until we reach the last one here. F of x to the n minus 1. It has to be odd index here, so coefficient 4. And the last one ever, only coefficient 1, f of x sub n. That completes our formula for our jet. And actually this should be, I just realized my little mistake right here, but this is f5 right here, because we only, f of x5, we only go up to x6 right here. So x6 is the last one being coefficient 1 on that. And this is x5. It makes sense now to be coefficient 4. Okay, and so now we're ready to really write it down right here. Delta x was a 1/6 and then divided by 3. So all together it's a 1/6 over 3, but 1/6 over 3 algebraically is the same as 1/18. Okay, that saves me some space with the algebra. And then f of x is 0, so that means we're looking at e to the 0 all square. Plus, now 4 times e to the, x1 on our chart was that 1/6. Okay, so 1/6 here is our x1, and then x2 is 1/3, and so on. So go ahead and, you feel free to pause the video to take note of your partition chart here, because I won't keep switching back and forth any longer. Okay, but now e to the 1/6 all square. Okay. And then now I'm going to have 2 times e to the 1/3 all square, okay, plus, and then now it's 4 times e to the 1/2 all square, plus, and then now it's 2 times e to the 2/3 all square, and then I'm running out of lines, so I'm going to jump down to my next line right here, plus, and now 4 times e to the 5/6 square. So this is the 5th one, okay, and the last one on our list here is only coefficient 1, so e to the 1st power square. That's how I can successfully substitute values into my Simpsons rule formula using 6 subintervals. Okay, so now again I am going to step back to my computer station to obtain a calculated answer, and I'm going to be right back. All right, and the answer I found using decimals, 1.46287,345,462, and a lot longer. And that is the answer I've had. So this is SS6, ladies and gentlemen. It's the approximation answer that came out from the Simpsons rule with 6 subintervals. Or in other words, you can think of this as so that's our answer for SS6, but that means the integral, the definite integral from 0 to 1 on our function e to the x, where the x will approximately equal to 1.4627 3, 4, 5, 462, and a lot longer. All right, so that's what it means that by doing any of these approximation methods. Okay. All right, and again, you have seen how I have done this in example 1. So I'm going to again show that here with example 2 right here. It's just the difference. The only difference between example 1 and example 2 is the different methods that we are approximating. Okay, but and so we found different approximates for using the Simpsons rule. So I already shared earlier that this actual answer, the computer knows it. We will know it too. Okay, but it's just right now we're on our way to build that foundation. So this integral has the exact answer in decimals, quite lengthy decimal actually. So 1.4626517. Okay, 4591, and I have to constantly, staring back and forth between the boards and the computer station of mine like that. All right, so now using SS4, okay, using the Simpsons method with 4 subintervals, we already came down to 1.463 76043. Okay, so that was our answer right here. So it came to quite close. So I guess if you're comparing the answer here with the trapezoid method earlier, then right at the same number of subintervals, then Simpsons rule wins a little bit of in terms of accuracy right here, because here the answer already came to as close as up to 2 decimals. Okay, within 2 decimals, the answer in 4 subintervals already came close enough in 2 decimals. Whereas, if I recall correctly, it was a 0.03 difference back in using the trapezoid method. Okay, and then now we're looking at SS6 right here. We came to even closer, 1.462. Okay, 3 decimals close. Okay, 462, and then 87, 345, 462, and that answer is still here from my other board, so it saves me from swinging back and forth between the board and the computer station. Okay, so these are the answer that for Simpsons rule using 4 subintervals and Simpsons rule using 6 subintervals. And so now Simpsons rule using 4 subintervals, as I underlined it earlier, it's close within 2 decimal places already, and here we're close up to 3 decimal places. All right, and so now again, but that's before. I don't really want to do a direct comparison, but at least what we draw here, what we draw as a conclusion, again, just like how we have seen earlier in that observation we have seen earlier, as we keep increasing the number of subintervals, we will keep getting better approximation. Okay. And so now, finalizing what I was saying earlier, that anytime you are doing the approximation work for a definite integral, there's always a good news. It's just, at least we know where we're heading. So the more subintervals we're doing, the better approximates we will get. Any technique came out to serve the purpose of getting an approximate for a definite integral. We will know a destination that we're heading to. Okay, unlike many other approximation methods to find answer for other kind of work right there, then sometimes there are the kind of approximation methods that we know we're approximating, but we're not even sure where our real target is. That's the idea. Here we know our real target. It's just we don't know how to calculate that actual final target, but we know that the more we keep increasing the number of subintervals, the better we're getting closer to the targets. That's one thing for sure. Okay.